Today's conversation is with Dr. Nicholas Rodd. Nick, who's originally from Melbourne, is a theoretical physicist and particle phenomenologist at CERN. His research mainly revolves around the understanding of dark matter, especially through indirect detection, as well as its connections to astrophysics and particle physics. Speaking with Nick provided us with insight into the daily life of a theoretical physicist and the challenges that scientists face nowadays due to external factors such as funding fluctuations and peer review. One of Dr. Rodd's highly emphasized points in our conversation was to always keep an open mind, an idea worth pondering about as we move through our undergraduate life. And here is our conversation with Dr. Nicholas Rodd. So please tell us about yourself and your career in science, and what are some interesting aspects of your research that you'd like to talk about. And of course, CERN is a place for that type of research. Yeah.
Oh, okay, fantastic. So that's a very open-ended question. So maybe let me try and bite that into little chunks. And please interrupt me if you feel I'm going too long on this, because there's a lot to say. So I'm actually also from Australia originally. I grew up in Melbourne. So when I was in high school, I had a rough interest in science, but I think quite similarly to the two of you, had no idea what that career would look like. And so didn't really think about it too seriously. I did, so in Australia it's quite common, at least when I was there, it may have changed to do 2 degrees. So I did law and science, and I thought the law would get me a job and I'd just do the science because it was interesting. But yeah, I did not particularly like the law side of things at all. And in fact, actually something that really changed my mind was I did an exchange to UC Berkeley in the US while I was an undergrad and did physics there and really enjoyed it. And then afterwards, I did something called, attended something called the CERN Summer Student Program. So if you're not aware of this, Manny, I would really recommend looking into it because it's a program where undergraduates from around the world come and spend 3 months at CERN and just do research and take classes. It was really a formative experience for me and solidified that is what I wanted to do, essentially. So after that, I did a master's in Australia. I moved to the US to do my PhD. I did a postdoc in the US, and then since then I've moved and I've just started as a staff member back at CERN a number of years after I was here as a summer student. So that's sort of my academic arc. And then specifically what I've been doing with my time is trying to figure out what dark matter is. So this is this mysterious substance that we know makes up the majority of the mass in the universe. It's more than 80% of the total mass we know, but beyond that, we have no idea what it is. And this isn't to say we're completely hopeless. We have lots of good ideas for what it could be, but it's a very challenging problem to resolve. So there's a lot of different directions that we're pursuing to try and figure out exactly what this missing substance is. So that's sort of the short of it.
Right. And you describe yourself as a particle phenomenologist, and that is obviously part of physics. But I feel like phenomenology to people our age is a lot less known than what a theoretical physicist or an experimental physicist is. So would you like to describe to us who a phenomenologist is and what is a day in their life maybe like?
So a lot of people, I know some people who thoroughly dislike the term phenomenologist. It's a somewhat vague term in some senses, but essentially what it means is you're looking for the phenomena that are caused by the particles, for instance. So in the field of particle physics, which is generally where we try and understand what is the real basic building blocks of the universe, the field separates into experimentalists and theorists. So experimentalists are the ones who are, for example, building these colliders or building instruments where we might discover these new particles and new interactions. And then the theorists are the ones who try and come up with try and either understand existing experimental results or try and predict what you might see in new experiments. Or even going beyond that, they may just try and think just vaguely about how the universe could even exist, or not necessarily vaguely, they often think quite precisely about what at its base level does mathematical consistency even impose on what the universe might be like. So that end of the spectrum is the really more, for example, getting into it's often called formal particle theory, or So for example, this is where string theory would live and this type of research. But then the group of theorists who is very interested in exactly how you can take ideas and apply them to experiment are the ones who are looking for the specific phenomena that comes from. And so that's where the field has the term phenomenology. So I'm someone who is a theorist, but very much interested in trying to make contact with experiment wherever possible. So that's sort of how my part of the particle physics research fits in.
So you mentioned that there are many challenges in determining what actually dark matter is. And so, Chris, can you try explaining what some of those are? What are some of the challenges that stump a lot of people, and how do you go about trying to solve them?
Good. So the fundamentally, we don't have a lot of information about it. I mean, in some senses, we know it's all out there. For instance, everywhere we look in the universe, essentially, all of the evidence comes from. It's basically like if we couldn't see the sun, we could potentially still infer that there was something there because you'd see all the planets orbiting around something. Now, you couldn't see where it is, but actually the speed of the orbit of the planets would tell you roughly how massive the sun is, because the more massive the star is, the faster the circular velocity. So actually you could start to do some inferences. I mean, putting the biological catastrophe aside, if the sun wasn't there, to try and figure out exactly its properties. And we can do this, essentially what happened was people were trying to study the orbits of stars and galaxies, and they found that it just was not remotely consistent with how much matter they could see. You could just add up how many stars were there, you could calculate how fast things should be moving, and they were moving way faster. And so from these sorts of measurements, we can infer that there is a whole bunch of additional missing mass. The problem is, these are observations made throughout the universe, like at the size of galaxies. And then our best guess is that this is just some new particle. So there's many orders of magnitude you have to bridge to go from the size of a galaxy to the size of a particle. Now you might say this is ridiculous, like why are you even thinking about that? But I mean, everything else we know in the universe is made of particles. So it's not a crazy idea to think that actually one new particle might solve this. And in fact, we have many ideas where that's the case. But the problem is in bridging these orders of magnitude, so many different possibilities could emerge when you get down to it. And basically the only thing we know for certain is that whatever this substance is, it does not talk to the regular matter very much, because otherwise we would have already discovered it. I mean, and to give a clear example of it, the reason it's called dark matter is because we do not see it in the optical spectrum at all. And so this means that whatever it is, it doesn't interact with light or if it does, it only interacts extremely weakly. So it's something that is out there. There are many possibilities, and if it does interact with us, it interacts very weakly. So that's just a flavor of the challenge that dark matter presents.
So the next question, it's about university. So for context, we're just about to start our undergraduate degrees in about 2 weeks. And so we just want to get general advice about university. What do you think, what's some advice you can give us to really get the most out of the undergrad years?
I mean, of course, it's such a personal part of this, and I really hope you both enjoyed it. It was a really fantastic experience for me, and I think it's I mean, of course, when you were doing high school, you were learning about many different things, and I feel that when I was going to university, I felt I was really going to specialize. But of course, the thing I would maybe, like at the outset, tell you to keep in mind is just keep an open mind about everything. For instance, like when I went in, I was sure I wasn't going to end up being a scientist, but I'm very happy with the path that I have taken, because I just listened to my gut at certain points and I wasn't enjoying what I was doing on the law side, and so I pivoted back. So keeping an open mind about that, I think, is very important. Beyond this, I guess one specific piece of advice I would have liked to have received when I was starting doing physics, learning physics at university, was at times, like some of the concepts you learn are maybe not as exciting, at least I thought, as some of the others. So you'll start learning about concepts like thermodynamics, for example. And I was often like, oh, this is not as exciting as learning about quantum mechanics. That's what I wanted to know about. But actually, it turns out like the people who have designed these courses, I mean, they are doing research often. And so they have an idea of what are the useful steps. And a lot of these things that I thought maybe weren't as interesting come up in my research all the time. So I think that actually just having some faith that all of these things have a place in this. If you do want to understand it, don't think that one part of it is just some less exciting than others in some aspects. I think if I had have known that ahead of time, I might have not had to relearn some of these things in as much detail as I had to.
Right. And you were doing a Bachelor of Science with law, and I feel like, to me personally, there seemed like sort of different aspects of our mind. And I again, personally wouldn't see myself being a person who follows qualitative knowledge or like social sciences. And as you said, it's just great to have an open mind towards it. What was it about social sciences or law specifically that sort of you thought wasn't great? And what was it about sciences that sort of attracted you, maybe?
So yeah, I guess two things I would say off that. I mean, the second thing is answering your question. But the first thing is it brings to mind the point that there are these separations. I mean, of course, there are these distinctions between the different sciences and the different pursuits we have. But I think ultimately, once you get into a career, at least in my own experience, I found that these divisions are more blurred than you might think. So for example, I know like when I was in undergrad, a lot of people, like in doing a law degree, you have to write a lot. You have to write a lot of essays, essentially just endlessly. I remember just writing. And so a lot of my colleagues who were doing just science were like, oh, you're spending all this time writing, you know, it's a waste of time, yada, yada, some people would say. But then when it comes to actually like doing the day-to-day work, one of the most important aspects of science is spreading the knowledge that you've uncovered. And the way that you do this is through presentations and through writing papers. And so I think, you know, these sorts of skills actually came back and have been immensely useful for me, even though ahead of time I feel there's sort of no way I could have guessed this. And this isn't to say that I think the best way to be a scientist is to go and get a law degree at the same time. But it's more that, I mean, I think that the sharp divisions really break down it somewhat. Once you're, you know, when you're doing classes, it can be quite regimented because you're just working on this specific part. But then when you actually pull this together into a career, you bring threads from everywhere. So I think that is something that is, I didn't appreciate ahead of time, realistically. But then, I mean, pivoting back to your original question about what excited me about one part opposed to the other, I feel that a lot of what law was, and this is, I mean, very personal, and I think that there's different aspects to that, but there was a lot of living in the ambiguity of language. And often I felt that if you really tried to pin down like what a judge had said in a judgment or exactly what a law meant, you couldn't. You would only get down to some fuzz where it was just about, you really couldn't exactly say because the language is inherently ambiguous. Did this phrase mean this or did it mean that? And a good lawyer would be able to exploit that ambiguity to their advantage, for instance. But I have to admit, I found that a bit frustrating at times because it didn't have the same, you know, logical consistency that I really enjoyed in science. And I mean, that's a very personal thing. I think that some people have a lot of fun, you know, with language and the way that you can play around with this, but I at times found that a little bit frustrating. So for me, I preferred, you know, where things were a bit more specific. But of course, I mean, even in research, you know, often there is no answer to some problems. Sometimes you'll try and, I mean, the exact problem in my research is what is dark matter? And I hope we will, but there's every chance we won't discover what that is in my lifetime. So it doesn't mean you get to have all the answers, of course.
You mentioned earlier that after you did your master's in Australia, that you went to America and did your PhD there. So we want to know, first off, how did you decide to leave? And second of all, how much of a necessity do you think travel is for a scientist at all stages of their career, like going to university and after the PhD and so forth?
Yeah, so this is actually something where I suspect the culture varies a lot between fields. So I would be very cautious about giving any advice, for example, to someone who is interested in pursuing biology, because I'm not exactly sure how it operates there. But I know in physics, it's a very international community. And as a rule, I mean, maybe 50 years ago you could, but as a rule, one of your career steps, you will have to probably do a big move and likely an international move. Now, if I was speaking to you probably 5 years ago, I would say you probably want to do a PhD outside Australia. The reason is it just opens more doors. Essentially, as much as I love Australia, it's very far from everywhere else. is one of its downsides. And so, for example, I mean, the two main hubs in physics are the United States and Europe. And essentially, like both of those two communities are regularly having conferences where they're all traveling around meeting with each other. And you're a little bit isolated if you spend your time in Australia. Although not completely, there's some really excellent science happening in Australia as well. So I think just getting into that network when you're a student was great. However, I am aware in the last couple of years of several people who did their PhD in Australia and have managed to move to great postdocs overseas. So I think that is potentially becoming more of an option than maybe it was when I was doing this. But yes, so that's sort of, I mean, a slight answer to the first part of your question. I mean, going towards travel, I think there's two parts to this. I mean, historically, travel has been an enormous part of at least in physics. I suspect in many other fields as well, where you just travel around for conferences all the time, trying to disseminate your ideas, learn about other people's new ideas, and form new collaborations. I do think that after the pandemic, there will be a reshifting. I've spent, as I'm sure the two of you have, a lot of my life on Zoom over the last 2 years. And as much as it's maybe I don't enjoy it as much as in-person conversation, I mean, it does open a lot of doors to people. For instance, some people cannot reasonably travel to conferences. They may not have the funds available. They may have family commitments, for instance. And so I think there's a general acceptance that it's less exclusionary to have more things online. So I think certain conferences will likely just move online and stay online. And this will be a change. And I also think there's been a move, at least I can say at CERN, there's been a bit of a push to try and reduce the amount of time we spend on planes. I mean, it's an enormous emitter of greenhouse gases, and there's a general consensus that, I mean, if there's something that we can have a real impact on, it's reducing the amount of travel that we do. So I think that there may be less travel coming out of the pandemic, but the fundamental motivation for the travel, which is connecting with people and presenting your ideas, that won't go away. If anything, some of that will move virtually.
Right. And now speaking about one of those great hubs in Europe, CERN. With your experience, how are large-scale international collaborations like in CERN? How are they usually organized and completed, and how do scientists get involved in them? Maybe how can students be involved as well with the scientists at the moment?
Good. So there's a lot to unpack in that. That's a good question. So I guess maybe just to bite off the easier part of the chunk at the end in terms of how students can get involved. I mean, the first thing I would recommend is maybe in the middle of your undergraduate degree, or maybe even have a few steps that I know can occasionally be competitive. Apply to the CERN Summer Student Program if you're interested in this. This is a fantastic way for undergraduates to get involved. And if this is something you're at all interested in, of course, talking to scientists is a great way of getting some perspective on this. But actually doing the day-to-day work of a scientist or sitting next to a scientist, watching them get frustrated when their code won't compile or whatever it is that they're up to, it gives you, I mean, there's just no substitute for just seeing it live, right? So I think that would be fantastic. But actually also, and unfortunately it would be too late for the two of you, but I mean, it might be something you may want to spread the word on. CERN, I believe, actually has a high school component where they encourage high school students to submit certain projects, and I think they have some interactions with them as well. Now, I think just potentially for historical reasons, it's really been focused on high schools in Europe, but I'm not aware of any reason why it shouldn't extend beyond that. So CERN is trying to spread itself to, its outreach in that direction, but those are the two activities I'm aware of there. So coming back to CERN as a broader organization, so, I mean, just to give some perspective here, so, I mean, CERN, I believe, hires many, many thousands of people, and if you include all the outside contractors who come in to work on various parts of the equipment, I think on any given day, there's ordered 10,000 people on site. So it is enormous, like it is a huge number of people who are there, and many of them are doing different things. So of course, one of the main aspects that is going on is building this giant collider and maintaining that and operating that, and then analyzing the data that comes out of this. But actually, for instance, like the group that I'm in, the theorists, we're a group of about 50 people, and we, a number of us think about the collider, but actually I don't spend much of my time at all thinking about the collider. just CERN historically has thought it was a good idea just to keep a bunch of theorists around to ask questions to, or also it's just to attract other theorists to come through as well. So it was generally viewed as just a good thing for the for CERN to have this group of theorists there. So I'm not day to day. If any big decisions are being made about the collider, no one's running it past me, for example. I mean, again, I spend most of my time thinking about dark matter, so I'm not sure I would be able to answer the questions anyway. But then in terms of like how such a thing is structured and how it is organized, I mean, it is incredibly complicated, even though I'm looking in on the outside. There's a huge hierarchy of people that need to be organized to make this to be achieved. There has to be these huge visions in terms of thinking about how these things will come to fruition. So for example, I believe CERN was first being, the LHC, sorry, CERN has existed since the 50s. There's been a number of accelerators there throughout the years, but the current accelerator there, the LHC, was first envisioned back in the 80s, I believe. And it took decades of people's vision, and they have to meld together creativity about what the future could look like, but a certain degree of pragmatism to actually make that occur. Just to say, it is absolutely not a foregone conclusion that these things will happen. I'm not sure if you're aware of it. There was a instrument called the Superconducting Super Collider that was going to be built in the US, they actually have started digging the tunnel. They had planned out a site. They had designs for this. They'd done lots of testing on the magnets, but eventually they just couldn't get it done. The whole experiment collapsed. So I think it is really an enormous achievement to bring these things together that requires a huge amount of planning that is very impressive. But yeah, again, I'm looking at this on the outside, so at least that part of it.
Right. Sort of changing the perspective a little bit here. Maybe a bit towards the more pessimistic side of science, if not so. Of course, just like any other career, science has many unpleasant aspects, one of which we've heard is job security. As after a PhD position, finding temporary jobs or permanent positions seems to be difficult, and that's one of those unpleasant aspects. Could you elaborate on that and maybe some other unpleasant aspects that you've faced or that exist in the field?
Yeah, so I think the job security is obviously something that is very problematic. And to be honest, as much as people are aware of it, I don't see any likelihood that in the next decade or two that will change very much. I mean, realistically, the state of the world is that generally science funding is not going up, I think, just across the world. And so because of that, I mean, if there's even less money, you have less positions to make permanent jobs. So, I mean, that's just a reality of this. And I mean, that's the most negative light that to put on this issue. However, I think that, like, to give some specific examples, I think that not finding a job is not the end of the earth, in the sense that, for instance, when I came out of grad school, my group of friends, I'm the only one left in academia. The rest of my friends are not in despair. Many of them have excellent jobs and they're very happy with and have fulfilling careers. I mean, the reality is, especially I can say for physics, is that a PhD in physics teaches you many skills. Like you'll usually learn a lot about how to solve a lot of maths problems, I should say again. And you also learn a lot of coding. And these skills are very useful. You're just like, you spend your whole time trying to tackle some very challenging problem using maths and coding often. And this is something that has uses everywhere. So I have friends who are working in the tech industry. I have a number of friends who moved into finance, for instance, because these skills are very sought after. So sure, the path in academia is narrow, but you don't just fall off a cliff. You often fall into a job that is paid much better than you would have had in academia anyway. So I think that if you go into it with that perspective, I think it's fine. And another way of spinning that as well is that if you just focus on the end goal, of course you can be disappointed. But, and I guess this is maybe even something I would go back to, advice for undergraduate is if you're just thinking about, getting the PhD, eventually getting some faculty position, all of, what you're looking for is in the future. But But I mean, ultimately, the reason that I was doing this is because I really enjoy the science. And, day to day, there are really satisfying aspects to the job, like understanding something new, having someone teach you something for the first time. It's a very satisfying experience. And so making sure that you're enjoying it along the path means that even if you end up doing something else, it's not like it's been wasted time. It's something that you really enjoy. So that's, the positive spin on that aspect. But of course, the other side, I think, is a real issue. The job, the constant moving around and the lack of job security certainly makes it harder for people to plan. For instance, I know a lot of my friends who I've left in Australia, most of them now would, some of them have houses, for example, and have started families, for instance. But I think in science, people tend to put this off a bit until they have more of a permanent footing somewhere rather than moving every couple of years. But I mean, it's a small sacrifice to pay for the other aspects. In terms of other negativities, there's definitely, I'm sure as with any career, there are many negativities. I think something that in science that we're really grappling with, and is an important issue that needs a lot of progress needs to be made on, particularly in physics, is the lack of diversity in the field. I think that this is just an absolute reality that the vast majority of people getting, for example, physics PhDs in the US are white men. And a lot of steps need to be taken there at all sorts of levels. But I think, this is a huge issue, and I don't mean to trivialize it by my next statement, but I think one of the steps that can be made towards doing that is making scientists more accessible. I think a lot of people never even think of pursuing a career in science because they have no idea what the day-to-day life would be like. And possibly they will never, they could never envision themselves in that career because of that. Exactly. I'm not going around maybe changing those people's mind. I'm giving my own background, but I think just having a wider accessibility to scientists is one way to hopefully help more people realize that this is a career they could actually pursue. So the sort of activities that you're doing, I think, is a good step in that direction. But
right.
This is a very complicated topic.
Yeah. So speaking of that, if you don't mind, could you tell us the process of your daily routine as a physicist? So that's an insight for future students.
Sure. Yeah. So I mean, often, and of course it'll depend at what career stage you're at. But often what I'm doing at the moment is, I can tell you what I did yesterday. I got up. I still have a number of collaborators in the US. I've received many emails from my US collaborators. So I'll have breakfast, then I'll respond to a bunch of emails that try and see what insights my collaborators might have had overnight. If there's anything quick I can resolve. If there's anything more complicated, I'll think about it for a bit and maybe suggest we have a meeting. I'll then maybe carve out some time. If there's some project I'm working on, I'm like, I want to calculate this today. I'll try and either write some piece of code or do some calculation on pen and paper. That's what I was doing yesterday morning. I was just trying to figure out some code. I'm trying to release some results that I've had publicly, and a colleague of mine has implemented it, and there's some funny features in that, so I was playing around with the code to make sure that worked. And then actually what I was doing all afternoon was, there's a giant process underway in the US at the moment called the snowmass process, where they try and figure out the future of particle physics. They do this every 8 years, I believe. And so they come together and we write a whole series of documents sort of outlining what the future of the field will be like for 8 years. Practically, this means I have a lot of writing commitments that are due. The one that I wrote yesterday was due tomorrow. So I spent all afternoon writing a short note on some future in research in my field. And so that was what I was doing most of the afternoon. Throughout that, though, I had another thing that you often have is just talks and meetings. So we had a group seminar yesterday at 4:30, and so I spent an hour just chatting to my colleagues about some recent papers they'd seen come out that they found interesting. So that's just, that was what I was up to yesterday, for example.
Great.
And so taking it back to some of the more unpleasant aspects, one thing has also been brought up many times in the conversations we've had is that there's definitely an environment of competition in science. And so we're just wondering, how do you think that takes form? How does that affect an individual scientist? Is it in applying for grants, for example, or is it competition for answering a certain question? How does it actually look?
Yeah, good. No, it's a good question, but I see it as I'm sure we all face a competitiveness in our lives, right? I certainly remember in high school being competitive. I mean, even not just on the sports field, but also in classes, you're trying to do the best. I mean, that spirit of competition is sort of everywhere, I find. And I think often in science, you get a lot of people who generally have been throughout their school careers have been good at what they do, and so they've continued down this path. But then, so eventually, you've got people who are used to doing quite well at things, but then they're tackling very hard problems, some of which we are not going to solve in our lifetime. So maybe the spirit of competition can get enhanced even further. So I think it's not just a negative aspect, though. I think that competition drives you forward. I mean, for example, recently I put out a new paper last night. Actually, I didn't post it yesterday. That's a longer story, but we put it out last night. But we essentially got beat by our competitors about a month earlier. Now it's not the end of the world. They didn't just do everything we did, but there was clear overlap between our papers. But I mean, this sort of thing happens all the time. But of course, one aspect of it is, it's frustrating that somebody beat you on this. But another aspect of it is it's very nice to know that something that you thought was interesting enough to spend a bunch of time thinking about, somebody else is spending about all this time. And I've actually had a number of conversations with the authors of that other paper, and there's a lot to talk about. So I think that there can be certainly positive aspects to that. On the negative side, though, is that, I mean, I personally had some run-ins where, for example, you might, somebody might have some model for what they think dark matter is, and I wrote a paper ruling out certain categories, like saying that certain categories of dark matter just cannot be doing what people thought they were doing. And I had quite an unpleasant experience where one of the people who wrote that was very upset about this and did not take that particularly well at all. But yeah, I mean, for instance, like, I just don't, as much as there are negative aspects to it and where they emerge, we should think carefully about how to get rid of them. I don't think the fact that there's competition there is a pure negative, and I think often it leads to good aspects. I mean, for example, in the case of the LHC, there's two instruments that do almost the same thing operating there, the two detectors. So the ring collides the protons together, but then there are the instruments where they do the collisions that actually try and analyze what comes out. And from the outset, they have two experiments working there, and they're in many senses in competition with each other. And I think that's been a really huge bonus for the field, because I think they've driven each other to new heights, and also given the field a huge amount of confidence that two very different groups of scientists are working on very different instruments and have often reached the same conclusions. Like, they both saw the Higgs, for example. And this gives us great confidence that it's not just some complicated systematic, but we really trust what's going on. So I'm sure, yeah, there really are negative aspects to this, but I think that the answer to that is not to try and get rid of competition. It's to try and find how it can, only the best parts of this can be enhanced, and the negative parts, we have some sort of release mechanism to deal with those.
Right. So, taking it sort of personally, for me personally pursuing physics, one thing that seems very hard in terms of being decisive what to pursue is this really subtopics and subgenres, if you'd say, of physics. And of course, as a person who hasn't been introduced to undergraduate physics, that's not really a true experience. But how does one decide what area of the physics to get in? What factors really influence a scientist on their way to their career?
Yeah, excellent question. And I mean, okay, there's a lot to be said on this. It's a really good question. So I guess the reality is you'll just never know until you're doing the day-to-day part of it. Because I think at some level, if you talk about the discoveries, and the most exciting parts, every field sounds pretty, pretty compelling. From chemistry to biology, if you're just there for the moments of discovery, that would be pretty thrilling, I guess. But you're not, like, what I didn't mention that I did yesterday was make some huge discovery, right? So this is something that doesn't come along so often. And what you really, I think, to really get satisfaction out of the job, you need to enjoy the day-to-day. You need to enjoy, like, the coding or the calculations that I do in my work, for instance, as opposed to just the eureka moments when you figure something out, and it's very satisfying. So I think because of that, and the problem is, from the outside, all you see are the discoveries at some level. Actually, what the day-to-day life is like is very hard. So I think one thing I would advise is try where possible to get involved in some research, even as an undergraduate. Like, try and work in, I mean, it's often challenging, like I know in theoretical physics, there's not so much for undergrads to do, in the sense that you need to have learned a certain amount of skills before you can do this. But that's not exclusively true. If you come in with some coding knowledge, there may be some problems that you can tackle. And more generally, though, I mean, if you look to the broader field, there's often areas where they just need manpower, like in the lab or whatever they're doing. And I really think it's a good experience just to get in there and try and do it. Just try and find ways of reaching out to this. Now, I would say, I think in general, the US, in my limited experience, does a better job at this than Australia, because I don't remember almost any of my friends getting involved in research as an undergrad. But then when I moved to the US, almost everyone there had done some research while they were as an undergraduate. But it may just be a cultural difference. I mean, just no one at the top thinks about it, no one at the bottom thinks about it, so it's just not happening. But I certainly think that there's no reason it couldn't. So I think if there's a chance for you to go and actually do some research, that would be great. If there isn't, then these sorts of internships like the one at CERN is the real way that you get some day-to-day experience. But then realistically, you will not have had experience in every single subfield. So at some level, you'll be going off your gut to a degree. And then ultimately, what would hopefully happen is that there was some seed of enjoyment that you had in this idea. And then by getting better at it and then building yourself up through the day-to-day working, so you'll learn to enjoy the rest of it more so. But of course, there's no guarantee. I mean, potentially some completely different career could have been the one that I would have gotten most enjoyment out of. But I'm not going to worry about that too much because there's nothing I can do about it. You moved along some path. And I think this broader problem also occurs on a smaller scale when you look at physics generally. I guess maybe, yeah, so beyond just looking for these specific research opportunities, I think something else that is useful is just to keep an open mind. When I started as an undergrad, the part of physics I was most interested in was particle physics, and I ended up working in it. But I often now have a lot of overlap with astronomy and astrophysics because that's what comes up in dark matter. And I am finding that to be a very, very interesting and beautiful field, and one that I just didn't think I had the appreciation for when I was an undergrad. So I think just keeping an open mind that you may actually find that the field you enjoy the most is not the one you're thinking of now, it can be useful.
So we sort of think of science as working by the fact that you constantly scrutinize each other's ideas just to make sure that it is correct, right? I'm curious, how does this actually take form? What does it actually look like? And how do you think the community operates as a whole? How does it all work together?
That's a good question. Let me answer a more modest version of this, like how does it work in my own particular field? So I think as an outsider, I would say, at least from what I read in the newspaper and talking to other people, it seems that peer review is seen as the metric or the gold standard for this. Something goes from just an idea to something that is scientific truth almost once it passes the peer review process. I don't really agree with that. I think that peer review has some aspects, but usually peer review will involve 1 to 3 other academics reading your paper. And then there is huge variability in this. You might get that one academic may have been asked to review your paper right in the middle of some very challenging time in their life, and they just don't have time to look at this. And that's just a reality. And so they'll just look at it, yeah, it vaguely looks okay, and it gets through peer review. I mean, this happens. And so then, the fact that this paper was peer reviewed doesn't mean anything. There's plenty of errors in peer reviewed papers and ideas that got passed. I mean, it may not even be that instance. It may actually be something that's very subtle that is only discovered a long time later. So for me, peer review, can help, and I think there's a lot of negative aspects to the way it operates at the moment, but it certainly can help. And I think but just because something's been published doesn't mean that it is correct. The broader way that this operates, and I think something I really like about physics, and I know that biology is actually moving this way as well, is that a lot of people will just post their papers as soon as they're done with them. on this website called the Archive. And there's now, I think there's also the bioarchive as well. This has become quite popular in the last couple of years. And this means that you just put the paper up as soon as it's done. So, I mean, one thing that I like about this is sometimes peer review can take over a year. And by the time your paper's out and you can talk to people about it, you did it a year ago. And so you're not as excited about it as you are. Whereas in our field, as soon as we're done, we just put it out and people can see it. And what happens here is sometimes people will send each other emails saying, your work is wrong. You forgot this, or this should have happened, or you've missed this. And in particular cases, actually, sometimes people will put papers up on the archive and they're in the form of, they write comment on this paper and they'll write something short saying this paper is wrong. And sometimes people write reply to, and there can be a bit of an online discussion about this. But like often what we're doing all the time is I look at the new papers that come out every day, and if there's something that's in my field, if it looks really interesting, I'm like, okay, I should read this. But if it looks too good to be true, I'll look at it and I'll be, hang on, have they missed something here, or what's going on there? And then I'll talk to some colleagues, and then eventually we may come to an agreement that I think that they've missed the point on some aspect of this. And so what happens in some senses, even if this comment on paper isn't written, as we move forward, there's sort of this collective knowledge that there's an issue in this earlier paper, for example. And sometimes maybe people will note this, but generally, if some really exciting idea turns out to be wrong, you'll know that that's the case in 10 years because no one's working on it anymore, for example. There's sort of, we figure this out collectively through conversations and emails and move forward through that. But also just to say that there's this grey area that it's not, a paper sometimes can introduce many ideas, and also sometimes the concept that they introduce, they're like, oh, we can think about it this way, can be very insightful, even if they then sit down and do the calculation and get it completely wrong. I mean, this can certainly happen. And so such papers can sometimes be very useful, for conceptualizing a way of thinking about something, even if the specific way that the person went about it was wrong. And I mean, I maybe don't want to go down this path, but just to say, I think at times, all throughout academia, certainly when you're actually working in it as a day-to-day job, and I think even down to the level of undergraduate and even in high school, there's this huge negativity I find associated with making mistakes at some level. And of course, the ultimate goal of this is to get things right. But I feel sometimes people beat themselves up too much about making mistakes because it isn't going to stop, I feel, at some level. No matter how senior you get, you'll occasionally make errors. I mean, of course, a useful thing to have is some system of cross-checks in mind to make sure that you catch as many of these errors as you can, like sanity checks before you go through. But even then, you can still make errors. And that's okay, I think, in my mind. I don't think that people should beat themselves up about this so much because ultimately these things get figured out. And if there was some seed of creativity in this original idea, often that can push through, even if there may have been some issue that was associated with that. But that's just in physics. Yeah, how it works more broadly is an interesting question.
Yeah. Do you think that process can be too sensitive where it will throw out some new ideas and creative ideas that don't necessarily follow what has been accepted previously when they actually might have merit to it? Does it happen?
Oh, I'm sure that there will be instances where people have been quite dismissive of really good ideas just because it's so far out of the box. I would say in my own field, because people are so, the possibility of what dark matter could be is so broad, people often come up with some wild ideas for exactly what could be going on. And I certainly think in the last decade, the field has become much more open to these types of ideas. And so I certainly think that there is usually a place for an acceptance that these ideas could be right. But of course, another aspect to this is that there's only so much time in a day. And so an idea could be interesting, there's a lot of interesting directions, but you can only work on so many of them. And so I think at times people might, okay, that's an interesting direction, but I'm not sure if that's going to pan out. So I'm not going to personally spend my time working on it, but that doesn't mean that I necessarily think that it's rubbish. I'm just hopefully, the person who worked on it or some other people will push it forward a bit further. I generally find that scientists are quite, in my own field, are quite open to out of the box ideas. But of course, as with any field, there's some main direction people are moving in, and there's just some inertia with that. There's some reluctance for everyone just to scatter off and grab at every new thing that comes their way.
And yeah, so we're sort of getting to the end of our questions, and one thing that we like to ask everyone is that, there could be plenty of people in our position, starting to become adults, and we're starting to look ahead to try to make plans for a future. And so we want to know what your advice is for young people. It could be about science, it could just be about life in general.
Yeah, again, great question, but there's so much that could be said. I say this because something that I said earlier, because I think that I've made this mistake at times. Is that don't always look for the end goal. I think that life is divided into these chunks where you're moving from this stage to this stage to this stage. And if you're too focused on just reaching the next stage, I think that you can miss the day-to-day enjoyment. I think back to my undergrad, I mean, some of the things you learn are just unbelievable. And if you're both passionate about the particular fields that you're going into, I think you're going to just really have some amazing times learning about these details in undergrad. There'll be some struggles too. I mean, the first time you sit down to do a calculation, you can't finish it in one day. Is some problem is a frustrating experience, but then it gives you some taste about what is life is like beyond that. And so, as much as you need to keep an eye on the future so that your plans don't just all fall apart, I really encourage you to make sure that you're mindful of the fact that you enjoy the journey as well.
Right. Sure. And as our final question, we are sort of trying to manage this and create this book of quotes from every scientist that we talk to, maybe one or two sentences, anything basically that you would like to say.
I feel a little bit put on the spot there. If anything, I would take the quote from something that I've said off the cuff while I was thinking earlier. I don't necessarily have something useful to say. I mean, if I could say final words, I would encourage the two of you to just keep pushing the project for a little bit, because I think it's a really good idea. And I mean, having these things on YouTube could give some high school students in future years access to the questions that you didn't know the answer to a year ago. So yeah, I'm really appreciative that you're organising this, and would encourage you to do so. Apologies, that's a cop out there.
Sorry.
That's fine.
Great. Well, thank you very much for talking to us. It was a pleasure.
Yeah, of course. And thank you for taking the time. And maybe if you continue down this path, I'll run into you again in the future.
Definitely. Right.
Okay.
Yeah.
Take care.
Thank you very much.